Welcome to the Unit 6A video lesson 2. Remember that the reading to go along with this video can be done before or after watching the video depending on your learning style. We're going to be learning how to write equations for lines and line segments, planes and other surfaces, and then lines in space, but mostly the lines and planes. The difference in these equations is they're going to be vector and parametric equations. Now you're thinking, why are we having to learn two types of equations at once? It's because it's really easy to go between them. Remember that vectors have two components. Their first component would be the horizontal component. Their second component would be the vertical component. Parametric equations have an x and a y equation. X is representing the horizontal, and y is representing the vertical part of the equation. So it's really easy to go from vector to parametric. So we're going to start with a vector equation and go to parametric from there. Let's talk about, given 2 points A and B, how you can find a parametric equation by starting with a vector equation. Let's just pick some points. Let's say negative 3, 4, 1, 6 as A and B. The first step in finding a vector equation is to use those 2 points to find a starting vector and a direction vector. Let's see what that looks like. Well, the starting vector is the vector that goes from the origin to point A. It basically is a vector that points to, we at least have to have one point in this vector equation that is on the line. Now, the direction vector is saying we need all of the points on this line, so let's find out what direction this line is heading in. So we need a vector going in the direction of that line. The easiest vector to talk about with that would be, look, A and B are both on the line, so the vector from A to B can be our direction vector. So we have to find those 2 vectors. A is easy because if you know the coordinates of A, then you know vector A. If this is negative 3, 4, it's vector 3, 4 with pointy brackets. If B is 1, 6, well, we would have to do head minus tail to get the direction vector. So now we have to create the vector equation of the form xy equals OA plus t times AB. So that's the initial point vector plus t times the direction vector. Now, where'd that t come from? Well, we have this idea that if we add these 2 vectors, we will get the vector going from the origin to B. So this vector plus that vector equals the sum of the vectors here. And that sum of vectors gets us one other point on the line. But if we want the equation for a line, that just means we need to find all the points on a line. So instead of just doing OA plus AB, we have to do not just one point, but all the points. We need to have a vector maybe going double the length AB. So we're multiplying by 2. Or we could have a vector going half the length of AB. So we'd multiply by 0.5. Those are our t's. Or we could have t being a negative number, and we could add AB times a negative number and get something back here. Do you see how by adding AB times any scalar, we can get to any point along this line? Now, next step. Simplify to get the vector form. So right now, we've got OA, which is our starting vector, and t times AB, AB being our direction vector. We can add these together by essentially multiplying t into that vector and then adding your alike components. Once you have that, you can separate the first and second components into the x and y parametric equations. This is the switch from vector to parametric. Let's see what that looks like in an actual problem. We're going to find the parameterization of the line through points a equals 2, 3, and b equals negative 3, 6. To get a basic idea of that, negative 3, 6. It's going to be here. A is 2, 3. So we're going to find our initial vector and our direction vector, and then this is the vector that's going to be shrunk or stretched to get all of the points along that line. Let us begin. So, x, y equals vector OA. Now remember, to get this you have to do head minus tail. So the heads is going to be A and the tail is the origin. Hey, that's 0, 0. What happens if you subtract 0? Nada. So OA you can just use 2, 3 because it's 2 minus 0 and 3 minus 0. Plus t, our parameter, which is going to be the scalar stretching and shrinking our direction vector, times the direction vector AB. Remember, head minus tail. B is the head, so negative 3 minus the tail of 2, comma, 6 minus the tail of 3. Next step, so we've gotten our 2 steps, we found the 2 vectors and we put them in together. So it's kind of 2 steps in one. Next, simplify. 2, 3 plus t times negative 3 minus 2 is negative 5. 6 minus 3 is 3. Further simplify, we can distribute. I meant to make that black. Distribute. Two, 3 plus negative 5t, comma 3t. Add the vectors. So the first component is 2 minus 5t by adding the first component here and the first component there. The next component is going to be 3 plus 3t by adding the second component here and the second component there. Basic vector addition. Now, they didn't ask for the vectors, they asked for the parameter equation, so we need to separate those components as x and y components into x and y equations. 2 minus 5t for x, 3 plus 3t for y. And that's the parameterization. Done! Now can you try the next one? Find the parametric equations for the line passing through A is 1, negative 4, and B is 7, 3. Use those same steps that we did before. Now pause it, try it on your own. Did you pause it? Did you really do this problem? Okay, I believe you. You paused it. We're good. Start with your equation. xy equals OA plus t times AB, starting vector and direction vector. Put those in using head minus tail. Here you are subtracting 0 from A, so nothing happened. Here you are subtracting B minus A. 7 minus 1 is 6. 3 minus negative 4 is 7. Distribute the t. Add the vectors. And lastly, we just put the x vector with the x. and we put the y vector with the y. And we have our parameters. Parametric equations. Huzzah! Now, how do we put it in space? Suddenly, instead of just an x and a y, we have an x and a y and a z. I'll let you read through this official book definition thing, but really all it's saying is you use the same steps as before, only now you have a z. And sometimes they'll actually give you your direction vector instead of giving you a second point, and it just makes life easier. This time around, we're going to be putting it in standard unit vector form instead of the component form we were using before. Slightly different, but it's the same idea. You're going to be adding alike terms instead of adding first components. So let us begin. Instead of x, y, and z, we're going to have xi vectors plus yj vectors plus zk vectors. Our initial vector is going to be written as negative 2i plus 0j plus 3k. Note this could have been skipped, but I don't because I don't want to accidentally skip anything. Parentheses, not pointy brackets, because it's just like a normal equation. Add t times head minus tail, 4 minus negative 2 is 6, I vectors, plus negative 1 minus 0, negative 1 j vectors, plus 3 minus 3 is 0 k vectors. Distribute the t. So we still have the negative 2i plus 0j plus 3k, and now we have 6t of our I vectors over here, plus negative 1t, or negative t, of our j vectors, plus 0t, which is just plain 0, of our k vectors. Add alike terms. Negative 2 plus 6t. You can't actually add those completely, but we can write negative 2 plus 6t is how many I vectors we have. 0 plus negative t is going to be negative t j vectors, and then we're going to add 3k plus 0k, so 3 plus 0 is 3 k vectors. If you wanted to simplify that a little bit more, you could get rid of some of those parentheses by making it subtract tj and add just 3k. And that is in standard unit vector form. For the next one, I'm going to be doing it in regular vector form. Things get a whole lot easier, though, because we are given the direction vector instead of given point B. This means you don't have to do any head minus tail. Because they gave it to you. This is AB. So this should be a bit of an easier one than last time, by a little bit. We're doing component form this time too, and I know that some of you prefer that, so. Same idea as before. Start with your initial vector, 0, 5, negative 2, because it's going from 0, 0, 0 to 0, 5, negative 2, plus t, our scalar, times the direction vector, and yay! They gave it to us. 1, 2, negative 3. We don't need anything else. We don't need to do the head minus tail. They gave it to us. Same steps as before. Distribute your t. Add your vectors. they didn't ask for the parameterization here. So this is the vector equation. But you could easily make a parameterization in 3 dimensions with an x equation, a y equation, and a z equation from here. X, y, z. It would be really easy to do, but they didn't ask for it, so we won't. Alright, now we have one more topic, but before we get to it, we have to do a mini review. Because not everyone has been taught about the standard of equation of a line in the same way. And if you haven't learned the thumb method, then you're missing out, and you'll get confused on the next page. So let's review the standard equation for a line. ax plus by equals c. Sometimes it's written as ax plus by minus or plus c, depending on what book you're looking at. But generally, I use this format. When you are graphing this, do not just put it into y equals mx plus b form, because that might have been the format that you were more used to. Because there's actually a really easy way to graph from the standard equation of a line, the standard form. And it is called the thumb method. It essentially means you're finding the intercepts. And you're finding the intercepts by covering stuff with your thumb. So here's our example. We wanted to graph 3x minus 2y equals 12. We're in Algebra 1 again. We're going to cover the 2y, because when you're finding the x-intercept, y equals 0, so that term would disappear. Cover it with your thumb. The y-intercept is the solution to this equation, 3x equals 12. Divide by 3, and you get that x equals 4. And that's your x-intercept. 1, 2, 3, 4. Done. Next, you move your thumb to find the y-intercept. Now, in the y-intercept, that means x equals 0. So, you're solving the equation, since the x term disappeared, negative 2y equals 12. Divide by negative 2 and you get negative 6, and that is your y-intercept. 2 points define a line, so once you have those 2 points, you can draw the line. And that, you can even add arrows. That is going to be the line of 3x minus 2y. In order to do this for our new topic, equation for a plane in Cartesian space, we are going to be using the standard form for the equation of a plane. Does that look a little similar to you? They moved the d over. I'm going to move it back over to the other side of the equation. But it's the same idea as the standard equation for a line. You just have z's. So what are we going to do? We're going to sketch the plane 3x minus 2y plus z equals 6 using the double thumb method. Same idea as before, only we have 2 thumbs. We need to find the intercepts. This time we're going to find the x-intercept, because y and 0 and z both equal 0. So we cover them with our thumbs. 3x equals 6. So x equals 2. 2, 0, 0 is our x-intercept. For y-intercept, x and z equals 0, and we just need to find a y. So you move your thumb so it's covering x and z, keeping the y term, including this negative. Negative 2y equals 6. Divide by negative 2, and you get negative 3. And lastly, for z-intercept, x and y are going to equal 0. and you just need to find the z term. Since these equal 0, they get covered up. 2z equals 6. The z-intercept is 3. So now you just graph them. 2, 0, 0, 0, negative 3, 0, 0, 0, negative, 0, 0, positive 3, and we will connect them. Now, in order to show this plane, we're not going to draw the whole thing because that would just be confusing. We're just going to draw a triangle of the plane and fill it in. And saying that's the plane of 3x minus 2y plus z equals 6. In class tomorrow, we'll talk about what happens if one of these intercepts doesn't exist, in which case instead of drawing a triangle, you sometimes have to draw a parallelogram. Where's my tongue? Draw a parallelogram if one of these doesn't exist. You'll see some examples like that tomorrow. For now, have a good evening. I'll see you tomorrow.